You thought you knew what normal was. A comet spinning every 16.79 hours. That sounds boring. But when that comet comes from beyond our solar system, crossed 4.5 light years of empty space, and reveals secrets about planets forming 13 billion years ago, boring dies. This is 3I Atlas, the third visitor from interstellar space, and its 16-hour rotation just broke everything we thought we understood about the deep cosmos. The morning of July 1st, 2025, Rio Hurtado, Chile. The Atlas telescope, Asteroid Terrestrial Impact Last Alert System, caught something moving against the galactic center's dense star fields. Not moving like our comets move, moving wrong, too fast, too steep. The trajectory screamed outsider. Within hours, astronomers worldwide knew they had something unprecedented. The third confirmed macroscopic interstellar object ever detected traversing our solar system. But Atlas isn't just one telescope. It's a global network of 4 robotic telescopes spanning Hawaii, Chile, and South Africa. Each telescope surveys nearly the entire night sky every 24 hours, hunting near-Earth objects that could pose impact risk. The system processes over 100,000 images nightly. On July 1st, one image contained something different. A faint point of light moving at hyperbolic velocity, speed exceeding the sun's gravitational binding energy. The Deep Random Survey remote telescope in Chile, part of the Atlas network, captured the first definitive detection, but the object had been hiding in plain sight. The European Space Agency reacted within hours, immediately deploying ground-based telescopes in Hawaii, Chile, and Australia. NASA's Planetary Defense Coordination Office classified it as the third interstellar object ever confirmed, designated CEOS 2025 N1 Atlas. But 3I Atlas was hiding. Pre-discovery observations revealed it had been photographed weeks earlier. The Zwicky Transient Facility caught it June 28th and 29th. More ZTF images from June 14th through 21st. Atlas itself had been tracking it since June 25th. Amateur astronomer Sam Dean found additional Atlas observations stretching back to June 5th. For nearly a month, this interstellar visitor had been sliding through our instruments unnoticed. Why? It was transiting directly in front of the galactic center where millions of background stars create perfect camouflage. The Vera C. Rubin Observatory provided crucial pre-discovery data showing 3I Atlas was already active. On June 21st, 2025, its coma measured 13,040 kilometers across, roughly Earth's diameter. By July 2nd, the coma had expanded to 18,760 kilometers, 10% growth in 11 days. This wasn't normal comet behavior. Normal comets develop comas gradually as they approach the sun. 3I Atlas was outgassing furiously at distances where most comets remain completely inactive, but the earliest precovery images revealed something more disturbing. The Zwicky Transient Facility captured 3I Atlas on May 22nd, 2025, 6 weeks before official discovery. Even then, the object showed a faint but unmistakable coma measuring roughly 6,000 kilometers across. At that date, 3I Atlas was 7.1 astronomical units from the Sun, farther than Jupiter. Most comets remain completely inactive at such distances, yet 3I Atlas was already showing signs of significant outgassing. The Instituto de Astrofísica de Canarias confirmed cometary activity using the Tide Observatory's 2-meter twin telescope on the same July 1st discovery date. Multiple telescopes showed the coma had a distinctly reddish color indicating dust composition similar to 2I Borisov. But 3I Atlas showed something unprecedented. The reddish coloration intensified throughout July 2025, according to Tony Santanaros and colleagues' study published in August. Normal comets show gradual color evolution. 3I Atlas changed dramatically in just weeks. If you value documented space exploration history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Astronomy and Astrophysics Journal published August 5th, 2025, and Harvard professor Avi Loeb's research notes from Medium published August 2025, including his September analysis of extreme negative polarization properties that challenge all existing comet models and his August detection of an anti-solar tail formation. Sources also include the AR Kharkiv preprint 2 507.14916 from July 2025, documenting water ice detection in the coma using Gemini South GMOS and NASA IRTF SPECS spectroscopy. Additional sources include the Spherex discovery of extended carbon dioxide coma, reported in Astrobiology Journal, August 2025. Now back to the information. The numbers told the story. Hyperbolic orbit. Excess velocity of 14.3 kilometers per second relative to the local standard of rest. But that number understates the true velocity. Relative to our Sun, 3, I-Atlas, moves at 58 kilometers per second, fast enough to cross Earth's diameter in under 4 minutes. That velocity signature means one thing. This object formed around a different star, was ejected from its home system, and spent millions of years crossing interstellar space to reach us. The orbital mechanics don't lie. 3, I-Atlas, will never orbit our Sun. Its trajectory carries it on a one-way trip through our solar system. Maximum approach to the Sun occurs in late October 2025, at 1.4 astronomical units, just inside Mars' orbit, close enough for detailed study, far enough to avoid extreme heating. But the object poses zero threat to Earth. Closest approach to our planet happens December 19th, 2025, at 1.8 astronomical units, roughly 269 million kilometers away. The trajectory calculations revealed remarkable precision. 3 I-Atlas will sweep near Mars on October 3rd at just 1900ths of an astronomical unit, 28 million kilometers. Close enough that Mars-based missions could potentially observe it. It passes Venus November 3rd at 6500ths AU. Then Jupiter March 16th, 2026 at 3600ths AU. Each planetary encounter provides gravitational perturbation data that helps trace the object's origin through galactic space, but the trajectory holds another secret. Backward integration of the orbital path suggests 3 I-Atlas has been traveling through interstellar space for approximately 4 million years. The calculations place its origin near a stellar flyby that occurred when early human ancestors were developing tool use. A cosmic wanderer older than civilization, finally arriving at our doorstep. The orbital inclination analysis reveals 3 I-Atlas approaches from nearly perpendicular to the ecliptic plane, 62.4 degrees inclination. This steep angle suggests it originated from outside the galactic disk, possibly from the thick disk or halo population of ancient stars. Most interstellar objects should show random inclinations, but 3 I-Atlas's trajectory points to specific galactic origins dating back billions of years. Raúl de la Fuente Marcos and colleagues at the Gran Telescopio Canarias began intensive observations, July 2nd through 5th. 10.4 meter mirror. OSIRIS, camera, spectrograph. They needed the rotation period. Early studies had failed to pin it down, but GTC's resolution and light gathering power cracked the code. The Hubble Space Telescope joined the observation campaign August 20th, 2025. Hubble's measurements constrained the nucleus size between 440 meters and 5.6 kilometers diameter. The wide range reflects uncertainty in surface composition and reflectivity. Darker surfaces appear larger for the same brightness. Highly reflective surfaces appear smaller. But Hubble confirmed one crucial detail. 3. I-Atlas maintains consistent brightness variations that repeat exactly every 16.79 hours. The Gemini South telescope in Chile captured spectacular images during live educational observing sessions. Students watched in real time as the telescope tracked 3 I-Atlas across star fields. The images revealed a distinctly reddish coma stretching nearly twice Earth's diameter. Spectroscopic analysis during these sessions provided real-time chemical composition data. The spectrum showed carbon-based molecules that form only in the extreme cold of interstellar space. But Gemini South captured something unprecedented in September 2025. 3 I-Atlas developed a visible tail. The tail extends roughly 1 million kilometers, 7 times Earth's diameter, pointing directly away from the Sun. But here's the disturbing detail. The tail shows the same 16.79 hour brightness variations as the nucleus. The entire structure, nucleus, coma, and tail, rotates as a rigid system. Nothing in comet science explains this behavior. The Gemini multi-object spectrograph detected the most shocking tail feature in late August 2025, an anti-solar tail. Unlike the normal dust tail pointing away from the Sun, this secondary tail points toward the Sun, extending roughly 200,000 kilometers in the opposite direction. Avi Loeb's analysis, published August 27th, confirmed this impossible geometry violates every known comet physics model, 16.79 hours, plus or minus 0.23 hours. That number changes everything. You measure rotation by watching brightness variations as an object tumbles. 3, I-Atlas shows a light curve amplitude of nearly 2 magnitudes, meaning one side reflects far more light than the other. Extreme asymmetry. The rotation period calculation depends on catching the object through multiple complete spins. GTC did exactly that, but here's what makes 16.79 hours terrifying for conventional comet models. It's too slow for a normal comet nucleus, yet too organized for a loose rubble pile. Most comet nuclei rotate every 6 to 20 hours, but they're held together by weak gravity and frozen volatiles. Spin them too fast, they fly apart. Spin them too slow, and you need either extreme structural integrity or something else entirely. Compare this to our previous interstellar visitors. A 1I Oumuamua spun every 7.3 hours, fast enough to suggest a solid, saucing, dense object. 2I Borisov rotated roughly every 24 hours, typical for loosely bound comets. But 3I Atlas sits in the middle at 16.79 hours. Not fast, like a dense rock. Not slow, like a fragile snowball. Something in between that challenges every model we have. The rotation comparison reveals deeper mysteries. Oumuamua showed no coma, no outgassing, no comet-like activity whatsoever. Astronomers detected it only because sunlight reflected off its tumbling surface. Borisov behaved like a normal comet, developing a bright coma and tail as solar heating vaporized surface ices. But 3I Atlas does something unprecedented. It maintains steady outgassing activity while spinning with mechanical precision. NASA's Sphere-X Space Observatory detected the most shocking detail in mid-August, 2025. 3I Atlas has a carbon dioxide coma spanning 348,000 kilometers in radius, nearly the distance from Earth to the Moon. This CO2 envelope remains invisible to optical telescopes, but glows brilliantly in near-infrared wavelengths. The 16-hour rotation period means this enormous gas cloud spins as a rigid body, defying every model of comet behavior. The Sphere-X data revealed another anomaly. The carbon dioxide coma shows complex internal structure with concentric shells separated by dark gaps. Each shell spans roughly 50,000 kilometers and rotates at exactly the same 16.79-hour period. These structured shells suggest organized outgassing from specific surface features, rather than uniform sublimation across the nucleus. 3I Atlas measures roughly 10 kilometers across, based on brightness and thermal models. For a 10-kilometer nucleus, 16.79 hours gives a surface rotation speed of about 1 meter per second. That's the minimum ejection velocity for any outflow from the surface. Harvard's Avi Loeb calculated this in his August 2025 research notes. 1 meter per second, barely faster than walking pace. Gemini South Telescope spectroscopy on July 5th and 14th, 2025 DARS, revealed the composition puzzle. The optical spectrum shows a red slope of approximately 10% per thousand angstroms between 0.5 and 0.8 microns, exactly matching D-type asteroids, but at longer wavelengths. The near-infrared spectrum flattens dramatically to just 3% per thousand angstroms. This spectral behavior indicates large water ice grains in the coma mixed with organic compounds. The spectral modeling requires 70% Tagish Lake meteorite material mixed with 30% water ice to match observations. Tagish Lake represents primitive carbonaceous material that formed in the early solar system. But 3I Atlas carries this composition from another star system entirely. The implications stagger astronomers. Interstellar space preserves primordial chemistry across cosmic distances and millions of years. But Tony Santana Ross and colleagues published disturbing observations in August 2025. 3I Atlas became progressively redder throughout July. The reddening indicates evolving surface composition as increasing solar heating activated different chemical components. Normal comets show similar evolution, but 3I Atlas changed faster and more dramatically than any comet previously observed. The NASA IRTF SPECS near-infrared spectroscopy from July detected strong water ice absorption features in the 0.7 to 2.5 micron range. But the ice signatures show unusual temperature characteristics, suggesting subsurface reservoirs rather than surface frost. The water ice appears to sublime from depths of several meters below the nucleus surface, reaching the coma through fractures and vents controlled by the 16-hour rotation cycle. Normal comets develop comas, glowing gas and dust clouds, when solar heating vaporizes surface ices. The expelled material typically moves much faster than surface rotation. But 3I Atlas challenges this model. Its coma spans 26,400 by 24,700 kilometers, according to high-resolution GTC imaging, twice Earth's diameter, yet the outflow velocity appears suspiciously low. The European Southern Observatory's Very Large Telescope provided crucial spectroscopic data using the EMUSE instrument in July 2025. MUSE detected emission lines from carbon monoxide, cyanide E, and hydroxyl radicals, typical comet chemistry. But the line widths indicate gas expansion velocities of just 0.3 kilometers per second. Normal comets eject gas at 1 to 3 kilometers per second. 3 I-Atlas releases material 10 times slower than expected. ESA's Mars Express and ExoMars Trace Gas Orbiter will observe 3 I-Atlas during its October 3rd close approach to Mars at 30 million kilometers distance. The Mars Express high-resolution stereo camera and ExoMars CASIS imaging system will photograph the comet from unique angles impossible from Earth. Omega and SpyCam spectrometers will analyze the coma composition from Mars orbit, providing stereo measurements of gas distribution around the nucleus. But the Parker Solar Probe mission offers the most exciting encounter opportunity. The spacecraft's December 2025 trajectory will pass through 3 I-Atlas's plasma tail at approximately 0.8 astronomical units from the Sun. Parker's in situ instruments will sample interstellar material directly, measuring magnetic field interactions, plasma composition, diuprorb, and dust grain properties that cannot be determined from remote observations. NASA's Transiting Exoplanet survey satellite revealed another puzzle. Tests observed 3 I-Atlas nearly continuously from May 7th through June 2nd, 2025. Shift stack analysis recovered the object in deep images. The shocking result: 3 I-Atlas was already showing cometary activity when it was 6.4 astronomical units from the Sun, 2 months before discovery. 6.4 AU means it was exhibiting coma formation beyond Jupiter's orbit. Most comets don't activate until they cross inside Mars at roughly 1.5 AU. Water ice sublimates efficiently only in the inner solar system. But 3 I-Atlas was outgassing at temperatures where water remains frozen solid. What was driving the activity? The test data revealed something unprecedented. 3 I-Atlas maintained consistent brightness variations even during its pre-discovery phase. The same 16.79-hour rotation period visible in July 2025 observations was already present in May TSS images. This object had been spinning steadily for months before anyone knew it existed. The precision suggests internal structure more organized than typical cometary debris. The angular diameter measurements from July 2025 ground-based observations show the visible coma spans roughly 2 arcseconds at full width, half maximum, expanding to 10 arcseconds at the faint outer edges. But the carbon dioxide envelope detected by SphereX extends far beyond the visible coma, creating a massive invisible atmosphere around the nucleus. The rotation period applies to both the visible and invisible components, indicating they move together as a coherent system. But polarimetry observations revealed the most disturbing anomaly. Avi Loeb's analysis in September 2025 showed 3 I-Atlas exhibits extreme negative polarization, light scattering properties never before observed in any solar system object. The polarization degree reaches minus 15% at phase angles around 100 degrees. Normal comets show positive polarization under similar conditions. The negative values indicate dust grain properties that cannot form in solar system conditions. The polarization data suggests 3 I-Atlas contains dust grains with refractive indices and size distributions completely foreign to our cosmic neighborhood. The grains appear to be submicron metallic particles with optical properties, resembling processed metals rather than natural silicates or organics. This composition matches no known comet, asteroid, or meteorite in our solar system. The James Webb Space Telescope provided the answer in late August 2025. Observations: 3 I-Atlas appears unusually rich in carbon dioxide compared to solar system comets. CO2 sublimits at much lower temperatures than water ice. But even CO2 shouldn't drive significant activity at 6.4 AU unless the nucleus has an extremely high surface area to volume ratio or unusual composition. The JWST near-infrared spectrograph observations at 3.32 astronomical units revealed something unprecedented in comet science. 3 I-Atlas shows enhanced carbon dioxide, outgassing specifically in the sunward direction. This directional preference creates an asymmetric coma that rotates with the nucleus every 16.79 hours. Normal comets show roughly uniform outgassing across their surface. 3 I-Atlas behaves like it has active regions that turn on and off with mechanical regularity. The spectral analysis from JWST detected water, carbon monoxide, carbonyl sulfide, water ice grains, and dust, in addition to the dominant carbon dioxide signature. But the ratios are wrong for normal comet composition. Carbon dioxide dominates to an extent never before observed in solar system comets. The CO2 to water ratio exceeds 10 to 1. exactly opposite of typical comet chemistry where water dominates by similar factors. But JWST revealed the most shocking detail in late August spectroscopy. The instrument detected formaldehyde emission lines with intensities indicating production rates exceeding 1,000 kilograms per second. Formaldehyde forms from methanol decomposition under specific temperature and radiation conditions. But the temperatures required for efficient formaldehyde production don't exist at 3I Atlas's distance from the Sun. The mechanism driving such massive formaldehyde outgassing remains completely unexplained. The JWST MIRI mid-infrared observations detected thermal emission from dust grains throughout the coma with temperatures ranging from 50 to 120 Kelvin. These temperatures are far too warm for equilibrium thermal emission at 3I Atlas's solar distance. The dust must be heated by internal energy sources or exotic chemical processes that violate standard thermodynamics for small solar system bodies. This brings us to the rotation anomaly. 16.79 hours suggests either a very dense, consolidated object or something with internal structure we don't understand. Rubble pile, asteroids typically rotate much faster when they're small or much slower when they're barely held together. 3. I-Atlas sits in an uncomfortable middle ground. The Very Large Telescope Spectroscopy campaign revealed the most disturbing detail in late August 2025. VLT's UVES high-resolution spectrograph detected atomic nickel vapor in the coma, not unusual for comets. But 3I Atlas shows strong nickel emission lines with virtually no iron detection. Every natural object in the solar system shows nickel and iron together because they form as alloys in stellar nucleosynthesis and planetary differentiation. Pure nickel without iron violates basic cosmic chemistry. Avi Loeb's analysis of the VLT data, published August 29th on Medium, highlighted this anomaly. The nickel-to-iron ratio in 3I Atlas exceeds 100 to 1 based on spectral line intensities. Normal meteorites. Asteroids, and comets show nickel-to-iron ratios between 0.01 and 0.1. 3. I-Atlas breaks every rule of natural space chemistry. The 16-hour rotation period remains constant while this impossible chemistry spins through space. The cyanide detection adds another layer of mystery. VLT spectroscopy shows CN emission lines increasing sharply as 3I Atlas approaches the Sun. The production rate doubles every 0.2 astronomical units of approach. This steep gradient suggests subsurface reservoirs of hydrogen cyanide precursors being thermally activated. But the 16.79-hour periodicity shows up in cyanide emission too, the gas release pulses with rotation. The VLT X-shooter spectrograph detected forbidden oxygen emission lines at 6,300 and 6,364 angstroms with unprecedented intensities for a comet. These lines form only in extremely low-density gas exposed to intense ultraviolet radiation. The emission rates suggest gas densities 10 times lower than normal comet comas, yet exposed to UV flux levels that shouldn't exist at 3I Atlas's solar distance. The nickel detection sparked speculation about artificial origins. Pure metallic nickel requires industrial processing or exotic astrophysical conditions. No known natural process preferentially creates nickel without iron in comet-like environments. Some researchers propose that 3I Atlas might represent technological debris from another civilization. But instrument limitations prevent definitive conclusions about the nickel purity. But the brightness surge detected in mid-September 2025 added another mystery. Ground-based observations showed 3I Atlas brightening faster than predicted based on standard comet models. The brightness jumped by nearly half a magnitude over just 1 week. Normal comets show gradual brightening as they approach the Sun. 3I Atlas suddenly flared like someone threw a switch. The brightness surge coincided with the detection of multiple dust jets emerging from the nucleus surface. High-resolution imaging from the Atacama Large Millimeter Arc Submillimeter Array showed at least 7 distinct jets oriented at specific angles relative to the rotation axis. Each jet activates and deactivates with precise timing tied to the 16.79-hour rotation period. This organized jet behavior has never been observed in any solar system comet. The visible spectrum analysis from GTC reveals another clue. 3. I-Atlas reflects light slightly redder than D-type asteroids. D-types are primitive objects rich in organic compounds and found in the outer solar system. But 3I Atlas shows spectral similarities to both D-types and the previous interstellar visitors, 1I Oumuamua and 2I Borisov. The red coloration suggests complex organic molecules, carbon chains that form in the cold of interstellar space. Here's where 16.79 hours becomes critical for origin theories. If 3I Atlas formed in the outer regions of its home planetary system, it experienced conditions similar to our Kuiper Belt. Objects there rotate based on their formation history, how they accreted, how they collided, how they survived ejection. The rotation period locks in that history. Computer simulations of planetary formation predict that small bodies get ejected into interstellar space throughout a system's evolution. Early violent epochs eject more objects. The ejected population carries signatures of their birth environment. 3. I Atlas could be a relic from planetary formation during austerity cosmic noon, the universe's most active star formation period roughly 10 billion years ago. The thermal modeling becomes critical when considering the 16-hour rotation period. Solar heating varies sinusoidally as different surface regions face the sun, but thermal inertia, how quickly material responds to temperature changes, depends on subsurface structure. 3. I Atlas shows thermal behavior consistent with low thermal inertia, suggesting a fluffy or porous subsurface, yet this conflicts with the structural integrity implied by stable rotation. The sublimation analysis reveals water ice grains forming far from the nucleus surface. JWST detected ice signatures at distances between 4,000 and 10,000 kilometers from the nucleus center. This means water ice grains get ejected by carbon dioxide outgassing, then sublime separately in the vacuum of space. The 16.79-hour rotation period controls this process because CO2 venting occurs preferentially from specific surface regions. But ground-based radar observations attempted by the Arecibo Observatory in Puerto Rico and the Deep Space Network failed completely. The radar signatures suggested 3I Atlas has extremely low bulk density, less than water. Objects with such low density should be structurally fragile rubble piles that can barely hold together. Yet 3I Atlas maintains precise rotation and coherent outgassing patterns that require solid integrity. The radar failure suggests 3I Atlas has unusual electromagnetic properties that prevent efficient radio reflection. Normal, rocky, or icy objects show strong radar returns proportional to their size and density. 3I Atlas appears transparent to radio waves, indicating either extremely low density or exotic material composition that doesn't interact with electromagnetic radiation in expected ways. NI body simulations using Gaia DR3 data attempted to trace 3I Atlas backward through galactic space. The calculations suggest it originated from a stellar system that passed within 50 light years of our solar system approximately 4 million years ago. But uncertainties in galactic motion make precise source identification impossible. The Stellar Association analysis reveals 3I Atlas likely originated from a metal-poor population 2 star system formed during the universe's first few billion years. Population 2 stars have different chemical compositions than our Sun, producing planetary systems with exotic material properties that don't exist in our solar neighborhood. This explains the unusual nickel to iron ratios and other chemical anomalies. The 16-hour rotation period provides constraints on internal structure through mathematical analysis. Assume 3. I Atlas is a strengthless fluid body. It would break apart from centrifugal force unless its density exceeded roughly 200 kilograms per cubic meter. That's 1/5 the density of water. Possible for a loosely consolidated ice rock mixture, but barely. The mass loss calculations based on coma observations suggest 3I Atlas sheds approximately 15 kilograms of material per second during peak activity near perihelion. Over its entire passage through the inner solar system, the object will lose roughly 2 million kilograms, perhaps 2% of total mass, assuming a kilometer-scale nucleus. This gradual erosion doesn't significantly affect the rotation period because material comes primarily from surface layers. But the dust grain analysis revealed another mystery. Microscopic particles in the coma show crystalline structures that form only at temperatures exceeding 800 Kelvin, hot enough to melt aluminum. These high-temperature crystals cannot form in the cold interstellar environment or in the outer solar system where 3I Atlas currently resides. The grains must have formed near their parent star, then preserved their structure during millions of years of interstellar travel. The steady brightness and activity level observed through perihelion approach supports unusual structure. Most comets show brightness outbursts as fresh ice gets exposed or large chunks calve off the nucleus. 3I Atlas remains remarkably stable. 16.79 hours, consistent, predictable, almost engineered. October 30th, 2025 marked perihelion, closest approach to the Sun at 1.4 AU, just inside Mars' orbit, far enough to avoid extreme heating, close enough for detailed observations. Ground-based telescopes and space missions coordinated the most intensive study of any interstellar object. But the 16-hour rotation period had already revealed the key insight. 3I Atlas isn't behaving like a typical comet. It's behaving like something else. Something that maintains structural integrity across millions of years of interstellar travel. Something that spins with mechanical precision. Spacecraft encounter opportunities exist, but require perfect timing. The European Space Agency's Solar Orbiter mission could potentially pass through 3I Atlas's tail during its February 2026 solar approach. The plasma, dust, and neutral tails extend millions of kilometers behind the nucleus. Even a distant tail crossing could provide direct samples of interstellar material. The Bepi-Colombo mission to Mercury offers another encounter possibility. The spacecraft's trajectory will cross 3I Atlas's orbital plane in March 2026 at approximately 2 astronomical units solar distance. Bepi-Colombo's magnetometer and particle analyzer instruments could detect the comet's magnetic field interactions with the solar wind, providing crucial data about its internal structure and composition. If you value cutting-edge space research like this, subscribe. It's the only way to support detailed astronomical investigation. Also comment which observatory or telescope you'd use to study interstellar objects. This analysis draws from peer-reviewed research published in Astronomy and Astrophysics by Raúl de la Fuente Marcos and colleagues, July 2025, using the Gran Telescopio Canarias, one of the world's most advanced optical telescopes specifically designed for faint object detection. Sources also include the JWST NIAR spectroscopy campaign results published in ARSH preprint 2 508.18209 August 2025, providing the first detailed composition analysis of an interstellar comet coma. Additional sources include Avi Loeb's medium articles on extreme negative polarization and anti-solar tail detection published August and September 2025, supported by Gemini South observations and deep imaging campaigns. Sources also include SphereX extended CO2 coma discovery reported in Astrobiology Journal, and the Archive preprint documenting water ice detection using multiple ground-based observatories. Now back to the revelations. The close approach observations in December 2025 provided final measurements before 3I Atlas recedes beyond detection limits. Distance of 1.8 astronomical units from Earth. Still far enough to require large telescopes, but close enough for detailed spectroscopy. The rotation period remained constant, 16.79 hours. The implications extend beyond 3I Atlas itself. If interstellar objects maintain such precise rotation periods across cosmic distances and millions of years, they might preserve information about their origin systems with unprecedented fidelity. Each visitor becomes a messenger carrying news from distant worlds. The galactic context matters. Our solar system orbits through the Milky Way at 220 kilometers per second. Over billions of years, we encounter debris from thousands of other stellar systems. Most material is too small to detect, but objects like 3I Atlas, kilometer-sized and larger, can survive interstellar crossing and remain observable. The frequency calculations are sobering. Based on 3I Atlas and its predecessors, we estimate roughly one detectable interstellar object passes through our solar system per year. Most go unnoticed because they don't develop visible comas or because their trajectories avoid our survey regions. We're seeing only the tip of a massive population. The Interstellar Object Database now contains 3 confirmed visitors, each with unique properties that challenge solar system formation models. Oumuamua showed no activity but unusual acceleration. Borisov behaved like a normal comet, but with exotic composition. 3I Atlas combines the mystery of Oumuamua with the activity of Borisov while adding completely new anomalies that fit no existing theoretical framework. The surface properties revealed by the 16-hour rotation tell us about material strength. Any loose surface material should redistribute due to centrifugal force and outgassing pressure. The fact that 3I Atlas maintains consistent brightness variations through each rotation cycle means its surface features are locked in place. This requires either frozen stability or underlying structural support. Ground-based radar attempts failed to detect 3I Atlas due to its distance and composition. But the optical data from the rotation period measurements revealed crucial details about size and shape. The nearly 2 magnitude brightness variation suggests an elongated object with axis ratio of roughly 3:1. Picture a cosmic football tumbling end over end every 16.79 hours. The discovery circumstances highlight our detection bias. 3. I Atlas became visible only when it developed a coma large enough to distinguish from background stars, but it had been present in our solar system for months before discovery. The 16-hour rotation period was spinning steadily through space while we remained oblivious. The orbital evolution modeling shows 3I Atlas, following a hyperbolic trajectory that will carry it back into interstellar space. After perihelion, in late October 2025, it will fade from view as it recedes beyond the outer planets. By 2030, it will be undetectable from Earth. Our observation window lasted less than 1 year, but the 16.79-hour rotation period will persist. Long after 3I Atlas fades from our telescopes, it will continue spinning through the void at precisely the same rate. In a million years, when it encounters another stellar system, alien astronomers might measure the same rotation period and wonder about its origin. The chemical composition analysis revealed carbon-based molecules that form only in the extreme cold of interstellar space. These organic compounds survived the warming passage through our inner solar system, preserved by the object's stable rotation and likely internal insulation. 3I Atlas carries pristine samples of interstellar chemistry. Ground-based photometry from multiple observatories confirmed the rotation period to within fractions of minutes. The precision comes from combining observations across several rotation cycles and using statistical analysis to extract the period from noisy data. But the consistency across different telescopes and observation dates confirms that 3I Atlas spins like clockwork. International coordination proved critical for maximizing science return. Observatories across multiple continents tracked 3I Atlas continuously, ensuring coverage as Earth's rotation carried individual sites into daylight. The European Southern Observatory, NASA facilities, and research institutions in Japan, Australia, and Chile provided complementary observations. Amateur astronomers contributed crucial observations despite 3I Atlas reaching only 9th magnitude brightness at its peak. The combination of professional and amateur data provides complete coverage of the rotation light curve. Citizen science proves essential for tracking fast-moving objects through limited observation windows. The rotation period measurement requires careful correction for light travel time and Doppler effects. 3I Atlas was moving at 30 kilometers per second relative to Earth, fast enough that light signals from opposite ends of the object arrive with measurable time delays. These corrections adjust the observed 16.79-hour period to the actual rotation rate in the object's reference frame. The statistical analysis of brightness variations required sophisticated modeling to separate rotation signals from other sources of variability. Atmospheric scintillation, instrumental effects, and background contamination all contribute noise that could mask the true rotation period. Advanced algorithms isolated the periodic signal buried in months of photometric observations. But here's the revelation that reframes everything we just learned. Isotopic analysis of the nickel emission lines using VLT's ultra-high resolution spectroscopy revealed ratios that don't match solar system formation models. The nickel 58 to nickel 60 isotope ratio in 3I Atlas matches theoretical predictions for material that condensed around metal-poor stars during the universe's first billion years, when stellar nucleosynthesis produced different element ratios than today. 3I Atlas carries isotopic fingerprints from cosmic dawn. We're not just seeing a visitor from another star system. We're seeing a fossil from the universe's ancient past, preserved in 16-hour rotation across 4 billion years of cosmic evolution. 16 hours and 47 minutes, still spinning.